Okay, so today we are going to start the proof of Fubini's theorem. We have actually already seen the statement in the previous video. But since we are going to prove it, so let's go through it once more. We are given a function f like this, whose domain is this Cartesian product of two copies of the set of natural numbers, and it's a real valued function. Then we are considering this infinite sum of all these functional values as the ordered pair n comma n varies over the domain, and this sum can be considered because this set is a countable set that we already know, and it is given that this sum is absolutely convergent. Then we have to prove that these equalities are true, and we have already seen what these equalities mean, so I am not going to repeat these things again. So instead, let's just start the proof as it appears in the text. Now, as it appears in the text, I am saying because this proof is you will see it's written here in the text itself that the proof is considerably more complex than the other proofs in this text, in this book, that we have so far come across, or the proofs that we are going to encounter later. So it starts like this. Let me start off by actually writing what Tao has written. What he writes in the beginning is this: this is a sketch only of an actual proof. This proof is considerably more complex than the other proofs of other results, and is optional reading, which means that if you want, you can skip this proof also. However, nothing is optional for us. So let's start. So at the very outset, the next line is this: the second equality, that is this one, follows easily from proposition 743. And proposition 364. But the question is how, and what is the second equality? In the second equality, we have our original infinite sum, and then another such infinite sum where as the input m comma n varies over our set, we are putting not the input itself in the function but switching the components, the coordinates of the input, and then putting that ordered pair in F. If you do that, still this is also such an infinite sum like this one. This is also absolutely convergent and its sum is the same as the sum of the original one. And Tau says this second equality follows easily from proposition 743 and proposition 364. Exactly how? Now we are going to see. In the text only this much is said. Okay, so for that we need to recall proposition 743 at least briefly. So let's do that first. So these explanations I am going to put within square brackets in this proof, because we will need to do it a number of times. Proposition 743 is of course your rearrangement of series, absolutely convergent series. And it's just your standard this let summation an p and absolutely, and yes, let's just state the proposition properly, because we anyhow are going to need it, so why do it briefly? Be an absolutely convergent series of real numbers and let f from n to n be a bijection. Then the series this is also absolutely convergent and they have the same sum, that is summation of a f of m is equal to summation of an. Roughly speaking, this just means that if we permute all the suffix values, natural numbers, or in other words, if we rearrange the terms, then we get the same sum. Then we get still an absolutely convergent series and the sum does not change. That's what this proposition says. Okay, now how are we going to use this proposition to prove that second equality? And this other proposition 364 it just says that having the same cardinality is an equivalence relation on the class of all sets. I don't see how that thing is used here. If you, however, spot what its exact use is in whatever we are now going to do, that is to prove the second equality, please let me know. All I see is this proposition being used. Okay, so let's now continue. So that means this is our proposition that we are now going to use. Now within another set of square brackets, I am going to justify this. The sum now I am going to justify the claim that the second equality is true. The sum is absolutely convergent. This is given. So by the definition of absolute convergence, we will have a bijection for which so and so things will happen. So let's just write that. Then there is a bijection G from the set of natural numbers to this set over which you are having the sum, that is n cross n, such that the series summation f of g of I as I varies over the natural numbers is absolutely convergent. That is just simply the definition of the definition of this sum. Absolutely convergent. Okay. Now we are going to consider another bijection, but this time from this Cartesian product to itself, a special bijection. Now we have already seen the statement of this theorem, that is, which just simply says that we can rearrange the terms of an absolutely convergent series to still have an absolutely convergent series and which has the same sum as the previous one. So we can just erase it. Now consider the bijection let me call this say G prime. You can call it H or in fact anything. Defined by this rule that G prime of n comma m is defined to be equal to n comma m. That is, it switches the order of the coordinates in this ordered pair. Then now we are going to do what? Now we are going to take the composition of this function and this function, and only one of the two compositions in this case is possible, because when you have two functions, you can say f and g, you can either form the composition f composition g or g composition f. In this case, however, only one of them is possible, and that one is g prime composition g. Why? Because when you put an input here, that input must come from this, because that is the domain of g, and that's because g is going to be applied first. Then g takes you from n to n cross n, and then g prime takes you from n cross n to n cross n itself. So this is a function but both of these things are bijections. This is a bijection, this one is also a bijection, so their composition is also a bijection. Then this is a bijection. Okay. Now from the definition of this kind of sums, when they are absolutely convergent, we know that it does not matter what bijection we choose to define the sum, that is, this sum is going to be equal to the sum of this infinite series, ordinary infinite series. And here this what g we choose, that it does not affect the final sum. That's what we saw in the previous video itself. After defining this kind of sums which are absolutely convergent as this kind of series, we in fact have already shown there that the sum is the same regardless of the choice of g. So now in place of g we are going to consider this, because this is also one such bijection from n to n cross n. Hence so we first write our sum, original sum. Now if you use this bijection, then this sum is equal to, it becomes an ordinary infinite series, where f of no longer g of I but this of I, g prime composition g of I, and I, like before, it varies over all the non-negative integers, that means natural numbers. Okay. Now we manipulate these terms a little bit. This is equal to, because function composition is an associative operation, so we can write this thing as f composition g prime of g of I. This we can do. Now if I write summation Will it make sense? Let's see. This step we have understood, it's just the definition, where in place of the bijection that we need, we have taken this bijection. This we understand, it's just simply composition of functions being associative. But what about this step? Okay, now to understand this step, do not think of this thing coming from the one above, but think in reverse. Say you have this sum, okay? Will you have this from this? That is the question. See, what about f composition G prime? F is a function from this to R, and G prime is a bijection from this into itself. Okay, so f composition G prime will be a function from, again, from n cross n to R, so if you have to write this, so you can see that this is again just like if it is a function from n cross n to R, for which we are considering again another such sum just like this one, where now in place of f we have f composition G prime. Okay, now in order to write this sum as an infinite series, you need a bijection from n to n cross n, and this time we are actually using this bijection, our original bijection. To write this sum as this one. So that's how you have got this. Now it makes sense. Okay, now it does not end here itself. Because we still have a composition we have this, which means now we know what G prime does. It interchanges the coordinates. So we have m comma n, and now finally if I write, because the way the second equality is given, if I slightly change this final sum, in the final sum we do not have f m comma n, but rather we have f n comma m, and here we have m comma n. But now if I write just that, will anything change? Strictly speaking, these two symbols look different, but you have to keep in mind that these names given to these natural numbers are they are variables and they are dummy variables. So It does not matter whether you call the first one m or n, you just have to maintain the pattern. That's what matters. If you have the first variable m and the second variable n here, then here it has to be switched. We have maintained that thing here. In other words, whatever you call a dummy, whatever name you call a dummy variable by, ultimately it does not change. It does not matter whether you are calling a variable x or y. If you maintain everything else about it and then you write the symbol slightly differently, then ultimately nothing changes. So that's how we have the second equality. So that's how it follows easily from the second equality. But there may be, if you are very minutely observing these things, there may be a doubt still lingering. I said at this step that think of this sum as your original sum. But of course not this one, but the one where you have n comma m here. And then write this as this. Okay? But the doubt you may have is that our original sum is given to be absolutely convergent. So there is, by definition, there is to be one such series for some bijection. We don't really know whether this sum is absolutely convergent, but actually we know. It is not given, but it has come out as a fact. Why? Because if your bijection is G, then for that specific bijection, this series is already absolutely convergent. And so by definition, this sum is absolutely convergent, and it is just simply this series, whose value will not change if in place of G you have some other bijection from n to n cross n. That's not the point here, but the point here is that although I have asked you to think in reverse, but still the existence of this G for which this series is absolutely convergent just makes this sum absolutely convergent by definition of absolute convergence of this type of sums. Okay, so there is no doubt, and we have completed the, you can say, proof of the second equality. So that's how it comes easily. It is easy, the other parts are harder than this. Okay, so that is what we have in the proof about the second equality. Now the author writes, we shall only prove the first. We shall just prove the first is same, first equality as the third one is similar. One is very similar. One just switches the role of n and m. Okay, so there in fact is really no need to prove the third equality. We just need to prove the first one. Okay, so for that, now we are going to give the sum of our given sum a name, that is the actual value. We are going to call it L. And that too, in proving the first equality, we are not going to do it in general for all the cases now itself. Right now we are going to restrict ourselves to the case where these values are all non-negative real numbers, and then we are going to handle the general case later. We first restrict ourselves to the case when this is always non-negative. The general case will be handled later. Okay. Let L be the sum of this sum. Just for the sake of not losing ourselves into these symbols and forgetting everything, right now we are under the restriction that all these f values are non-negative real numbers. We do not have negative terms now in this sum, and also of course we are under the hypothesis that this sum is absolutely convergent, and the actual value of this sum is, we are calling it L, capital L. And now the very next thing the author does is he claims something. Again, one can easily prove this claim. Yeah, but after calling this L, we repeat what we want to do. We want to show that the series, which is actually double series, converges to L. That means it's a series of a series. And now Tao makes this claim. One can easily, easily, of course, easily. This, strictly speaking, jokes aside, these actually are not very difficult. The only thing is that they are very messy. If you miss just one simple point, things can go haywire. One can easily show that for any finite set. Okay, so first he is writing the summation this, but now our input ordered pair varies over x is less than or equal to L for all finite sets. Finite sets X which are subsets of n cross n, and professor asks why, and now we have to answer why. So today in our video we are going to answer this, and the rest of the proof we are going to continue in the next video. Intuitively you can almost see why, but still we have to rigorously answer, and that rigorous answer goes like this. With the bijection, G, with the bijection I wrote now, with a bijection it will be, because we don't really know what G is, but we know that a bijection G exists because this is absolutely convergent. Because of that, with a bijection G, we have okay. Now do not forget that now our f values are all non-negative. That means these are also all non-negative, because the G of i's are nothing but these ordered pairs. So where all the ordered pairs are being accounted for in this G of i's, and that's why we have chosen a bijection, so that we get a one-to-one correspondence. Okay, now the next thing is this. Since f of G of I is non-negative for all natural numbers I, proposition 638 okay, let me first write the things down, and then I will before I erase this part, let's again see what this part is saying. It is saying that if we take any finite set X of our set over which the entire sum is given, and then take the chunk of the sum on that finite set, then of course this is going to give us some value. That value must be less than or equal to L, where L is the original sum. Okay, now what is it that we are recalling? Proposition 638. Chapter 6 is on sequences, and this proposition is about convergence of a monotone bounded sequence of that thing. Convergence of a monotone bounded sequence or monotonically bounded sequence, and proposition 731. Chapter 7 is about series, which is convergence of a series of non-negative real numbers. We need to recall these things. Okay, we will do that. Okay, so these propositions do what? They imply that summation f of g of I as I varies from 0 to k is less than or equal to L for all natural numbers k. Okay, now what the hell is this? Let's see. This part is nothing but just simply the definition of the absolute convergence of the given sum. So there exists a bijection G for which this series is absolutely convergent, and by definition this sum is just this series. Okay, but now we take into account this additional restriction that all the terms are non-negative real numbers. So these are all non-negative real numbers, that is greater than or equal to 0 for all natural numbers I. Okay, now proposition 638 and proposition 731 together imply that this thing is less than or equal to L for all natural numbers k. You can see that this is a finite series. Now what is going on here? So we start off with this series. Remember that we are calling the value of this sum capital L. So that means this series converges to capital L. So let me erase this part and then I will start explaining from here. So that means this is equal to L. But this infinite series is not just any infinite series of real numbers. It's a special kind of infinite series where all the terms are non-negative real numbers, and we have a result for convergence of such series, and that result is this 731. What it says is this, that such a series is convergent if and only if the sequence of partial sums, that is, if you take any natural number m, this is the sequence of partial sums of this series. Such a series is convergent, all of whose terms are non-negative real numbers if and only if the sequence of partial sums is bounded, especially bounded from above. Clearly, because all the terms are non-negative, all these sums are going to be non-negative real numbers. So all of them are greater than or equal to 0. So these terms are all bounded from below by 0. But if they are bounded from above by some fixed real number, then only this series is convergent, and conversely, when such a series is convergent, then the terms are bounded above by some positive real number, non-negative real number. Okay. Now this is one such series, and it's already given that it is convergent and it has value L. So by this result, this sequence of partial sums of this series is bounded from above, and in fact actually by L. And we know even more than this about L. What is that thing? And that thing comes from here. What this result says is that if we have, say, a sequence of real numbers that is monotone increasing, okay, monotone and increasing, which means that we have this. It goes like that. At the same time, the sequence is bounded from this side also and also from that side. Okay, from this side, of course, it is already bounded by the first term itself. We need not mention any other lower bound. But there is an upper bound. Okay, all the terms are less than or equal to that upper bound. Now, such a sequence is convergent if and only if, if and only if there is one such upper bound. And we also know what the limit is. The limit is the supremum or least upper bound of the sequence. Now when you are considering, okay, so what does this result have to do with this series? That is because since we are considering non-negative terms, so the sequence of partial sums will be monotone increasing. Why? Because if you say consider this particular term for some particular natural number m, say, then if you want to have the next term in this sequence, you will add one extra term, and that extra term is f of g of m plus 1. Now whatever this thing is, whatever real number it is greater than or equal to 0. So adding it to this thing either keeps it the same in case this is 0 or increases it in case it is positive. So that way this sequence of partial sums is a monotone increasing sequence. And because it's given that this series is convergent, which just simply means that this sequence of partial sums is convergent, so it will converge to the least upper bound, and the least upper bound of this sequence, and that least upper bound is L. And because it's the least upper bound, it's an upper bound after all, no? So that is why all the terms of this sequence of partial sums are going to be less than or equal to L, simply because L is their least upper bound and hence an upper bound. So we have just simply written that if you vary k, you are getting the terms of this sequence of partial sums. So that way all the terms are less than or equal to the actual sum L, and which in fact, even if one does not go this rigorously, you can just simply think of it casually. No, you are having a series where all the terms are non-negative and the sum is L, then if you are considering a finite part of this series, then that sum obviously must be less than or equal to L, because other non-negative terms have been added to get to L. So if you remove many of them, then you are going to have smaller terms. That's it. So this is the justification of this part. Now we continue. And keep in mind that this is still something we are doing, not it's not there in the text. In the text something else has been shown. It's about that sum over that finite set X. The finite set will come, so now we are going towards it. Okay, so we have started our explanation from here. We have reached here, and in order to explain that, I have messed up the thing here a little bit, but you understand. Now we are going to continue from here. Okay, now we come to that finite set X. Now for any finite set X, X, which is a subset of our Cartesian product, what do we get? G inverse X is finite. Why? And as a short explanation, I have written C proposition 3614, I think, yeah, properties of finite sets, that too part D. Oh, and in its own explanation, then still within another set of brackets, we can write this. In fact, what is our G? Our G is a bijection from N to N cross N, our original G. This is a bijection so G inverse from N cross N to N, first of all it exists because G is a bijection and this is also a bijection. Okay, so G inverse, now if we restrict this bijection to X, what is X? X is the finite subset of this. Then the restriction itself will be an injection, an injective or one-to-one function, because when you restrict a one-to-one function, the restriction is also one-to-one. But if we also modify the range, say in place of N, I take G inverse X, that is the image of x under G inverse, just that. Then I get onto also, it is surjective as well. So this is a bijection, and that is why G inverse x is finite, because x is finite, and in fact they have the same number of elements also, same cardinality. So for any such finite set x, this is finite, and so okay, now finiteness of this will give us what? There is a k1, oh, there is a natural number k1. I could have put some more effort to memorize these things and then write without looking at this, but that is pointless, no? We just need to understand what these things actually mean, such that this G inverse x is a subset of this set, the set of all natural numbers that are less than or equal to k1. Okay, now finiteness of G inverse x makes it a subset of a part of the set of natural numbers which does not skip any natural number. It starts from 0 and reaches one end. Why? Let's take one small example. Say G inverse x is, we don't really know what this set is, but because it is finite, and note one more thing, that G inverse x will contain which type of elements? Natural numbers, after all, because G inverse is a function from n cross n to n. So maybe G inverse has objects which look like this, say only 3 elements, okay, 0, 1 and 100. Then it's a subset of the set of all natural numbers less than, or you can take 100 here, or say you can take 200 or 1000. The point here is that whatever G inverse x is, it does not matter how many natural numbers it has, or what natural numbers in fact it has. That also matters, not just the number of elements but the actual numbers themselves. You can take the largest number here in place of k1. So G inverse of x has skipped many natural numbers between 0 and 100. This has not skipped any natural number between 0 and 100. So that is why this is bound to be a subset of this. Okay. But now what? Now the next thing, so yeah, now comes the real argument. So let me first write the equations and then I will justify. Now finally we have come to the sum about which the author has claimed something, that is this sum, a finite sum. This is equal to summation f of g of I as I varies over g inverse of x, and that thing is less than or equal to summation of f of g of I as I varies from 0 to k1, and this thing is less than or equal to L. Yeah, there is nothing else to be said here, so let me get rid of this part. Now this is less than or equal to L. Okay. And as an explanation for these things, within brackets we write recall proposition 7.1.11 part C, and note that G from G inverse X to X is a bijection. Okay, now we need to really recall this proposition and this part in fact. So let's do that, because otherwise we will not understand why this thing equals this thing. So it says its own statement is this: X is a finite set So I am just writing the essential parts. X is a finite set. F is a real valued function on X. So it is one of those results which are the properties of finite series or finite sums over finite sets. It's that part, that thing. And G from Y to X is a bijection. Then how G inverse X is finite, that we have understood, so this is not needed anymore. We just need this so part. Then this ordinary sum of the f values as x varies over the finite set X is equal to another such sum f of g of y, where y varies over y. So this is proposition 7.1.11c. Okay. Now let us try to understand what is happening in this step. In place of this sum you have this thing. Okay. Let's match everything. Here you have a real valued function f. We also have a real valued function f from x to r. Just like here you have f from x to r, here also you have f from x to r. The only thing you should remember is that this x, our x, is a finite subset of n cross n, and this f that you see here is actually a restriction of our original f, whose domain is this entire n cross n, to the set x. But f is after all real valued, because otherwise sums, these things don't make sense. Okay, so that means we have f, here also we have f, and here the input is x. Our input looks like this because the elements are like that. Okay, now what about the function g? G is g, again g. I think that's why I have chosen g here. So now our g, just like here g is from y to x, our g is from g inverse x to x. And definitely this is a bijection. I am not going into why this is a bijection, this you can understand. Our original g was a bijection, and this one is also a bijection because of that. Okay, so that is why we can replace this sum with this sum, where in place of f of the input we have f of g of something else. Y is there. In place of y we have written I, and in place of y here we have I, and this is our set y, capital Y. Okay, so that's why we have this step. It's justified. Okay, now comes the next thing. Now this is an actual finite series, because although this was also a finite series, but it was a sum over a finite set where no order was specified. Here however there is a specified order, and that order is being specified by g. And okay, no, I cannot say that also, because no, this is okay, what I said just now is not entirely correct. Just like this is a finite sum, this is also a finite sum without any order being specified. But the point is that what is g inverse x? G inverse x is a subset of this set. We have n here, but I am writing I there. Okay, so as you are going to consider the values of I that you have in G inverse X, those values are present here also among all the values from 0 through k1, but not possible, not necessarily all the values, maybe some of the values. Actually, it may also be the case that G inverse of X is actually equal to this set, but it may also be the case that this is a proper subset. Okay, so this inequality is a consequence of the fact that possibly not all the i's that you see here are appearing here. However, whatever i's are in fact appearing here already appear here also, and maybe some extra i's. And another fact, that these terms are all non-negative. That is why if you do not have anything extra on the right side, then fine, the sum, they are the same sum. But if you do have an extra term, that is an extra non-negative term, because of which the sum may increase, and if you really have a positive extra term, the sum definitely increases. In that case, you have strict inequality. And we have already shown before that this thing, which is a term in the sequence of partial sums of our original series, is less than or equal to L. So that's how you have this sum less than or equal to L. That's what the author was saying can be easily shown. In this mess of rigorous detail, it looks like these things are quite complicated, but if you sit down and think about it just a little casually, it's not that difficult. So that's how for any finite subset X of n cross n, if you look at finitely many such terms and take their sum, then that thing is less than or equal to L. So we have justified the first why question asked in the proof. Now next many more such why questions are going to come, so which we will handle when we continue this proof in the next analysis video. And I end things here itself for tonight, and the next update is this coming Tuesday. And because we have again gone through the cycle once more by going through graph theory, so on Tuesday let's go back to permutation groups from Herstein. So that's just it. I wrap things up for tonight. So see you on Tuesday with permutation groups. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.